Let's take an example. Okay. Okay, let's take a look of this case. Let's take a look of this case. So this is the operator, right? Is there a left identity? Is there a left identity? Yes. What is the left identity? So light is the left identity, right? If you apply light on the left-hand side of light, then you get light. Light on the left-hand side of dark, you get dark. So light is the left identity. Is that okay? Do we have a right identity? Do we have a right identity? Yes. Light is also a right identity. If you apply light on the right-hand side, so light cross light, you get light. Dark cross light, you get dark. So when you put light on the right-hand side, you don't change the result. Then it is a right identity. Is that okay? Good. How about this one? How about this one? Is there a left identity? Yes, there is a left identity. Beta is a left identity. So the property of a left identity is that you apply it on the left, so you get this one to be the same. Same. Is that okay? So this is a left identity. So this is a left identity. And here, this is delta. Delta is also a left identity. Is that okay? Delta is also a left identity. Because delta alpha, you get alpha. Delta beta, you get beta. Delta gamma, you get gamma. Delta whatever, you get whatever. That thing. So it is a left identity as well. But on the other hand, there is no right identity. Nothing that is alpha, beta, gamma, delta here. Nothing. Okay? So what does it mean? So in general, in an algebraic system, you can have multiple left identities or multiple right identities. Or you may have no left identity, you may have no right identity. Actually, you may have no identity at all. So for instance, let's take a look of this case. This is an algebraic system, n plus, right? It does not include the integer 0. So there is nothing that s to itself is equal to itself. So there is no left identity and no right identity. Is that okay? Is that okay? Good. But then there is something interesting. Okay. But then what? But then, so this is an interesting case, or lemma, or theorem. Okay. So if in the algebraic system A star, there exists some left identity. Let's say E and some right identity F, then E has to be equal to F. And such an identity is unique. So in that case, we call E the identity. Okay? Is that okay? So we have seen examples that can have a lot of identities, or even no. But this is a theorem. It says that if there is some left identity, and there is also some right identity, then this whole thing has only one left identity and only one right identity. And they have to be the same thing, the same element. Okay? Reason, the proof is very simple. Okay? The proof So to prove E is equal to F, this is it. So let's take a look of what happens if E is a left identity, F is a right identity. Let's take a look of what is E star F. What is it? So F is a right identity, right? So F star E is equal to E. It doesn't change. Is that okay? But E is a left identity. So E star F is equal to F. So good. So first of all, we know E has to be equal to F. Is that okay? And then let's see if there can be any two possible left identities. So for instance, let's say there is E1 is a left identity, and let's say there is E2, there is a right, there's another left identity. Is that okay? Now, if they are both left identity, then we must have when they operate on the same item, it has to be the same, right? So if they operate on F, they have to be the same, right? Right? But in that case, what? In that case, F is a right identity. That we have just shown. So this is going to be equal to E1, and this is going to be equal to E2. Is that okay? So the identity. So in that case, when there is some left and some right, the two identities has to be the same. And what? And there is only one left identity, and there is only one right identity. So it is unique. It is unique. And then this is the case. Okay, this is an example. So in this case, we really have one right identity and one left identity, which is light. The other one cannot be. Okay, it is unique. For this one, well, this one does not fit the theorem because it doesn't have a right identity, so it doesn't matter. And then how about this one? Let's see. Let's see. How about this one? Do we have an identity? Empty string. So if you consider binary strings that contain some string, a special kind of string that has length 0, let's call it empty string. Then you add an empty string on the left-hand side or empty string at the back. You don't do anything. So it is an identity. How about this one? Do we have an identity? Well, no. Okay, no, it's not there. Okay, you can think of so conceptually, minus infinity is something that you want. But minus infinity is a concept. It is not a real number. You cannot find a real number that is called minus infinity. So there is nothing there that makes it work. So there is no identity here. Is that okay? And how about this? So how about this and then multiply? So this is a multiply. Then we have an identity. Yes, 1. 1 is the multiplicative identity. Okay, that's it. So if it satisfies, okay, is that okay? So now we understand what is meant by identity, and then we can, and then if an algebraic system is a semi-group together with a unique identity, so the left identity and the right identity the same, a unique identity, then it is called a monoid. Is that okay? And finally, we can define what is a group. Okay, so what is a group? A group is something. A group is a monoid that together with an inverse. So what is an inverse? So inverse is a simple idea. So okay, let me change a little bit. So this is a definition. Okay, so we say an element B in A is an, okay, is a, let me write down first. Is a left inverse of an element A in A if B star A is equal to E. Okay, so So here, we are going to assume that we are looking at a monoid to begin with. So we are assuming that A star is a monoid with identity element E. Okay. Then we can define what is called the left inverse, and then also what is a right inverse. If okay, so we are going to define what is meant by inverse. So inverse is something that maps you back to the identity. So if we focus on the element A, and then if it happens that there is some element B such that B star A is equal to the identity E, then we call B the left inverse. Is that okay? So it is like if you do B on the left-hand side of A, you cancel the effect because it becomes an E here. E is like a 0 in the plus or 1 in the multiplication, right? So it's like you are doing the division by A if you multiply B on the left-hand side when you are doing the multiplication. Or it's like you are adding the minus of that number if you are doing the addition. Is that okay? And similarly, an element C in A is a right inverse. If you apply C on the right-hand side of A, you get back to the identity. Is that okay? Okay. So a group is defined. Okay. Okay. Is that okay? So far, okay, right? Now, we also have an interesting theorem. Okay. Okay. So we can define we can define what is a group here. Of perhaps an algebraic system A star is a group. It's called a group. Okay. If the following are all satisfied. So if first of all star is a closed operation, star is associative, there exists an identity so let's say E, and then for every element A in A, okay, there exists a left inverse. Okay, so this is the definition of a group. So these first two, you get semi-group. If you have the first three, you get a monoid. And you have the first four, you get a group. Is that okay? Is that okay? Now actually, this is one way to define a group. In some textbook, this is rather than writing there exists a left inverse, you will say there exists a left inverse and the right inverse and the two inverses are the same. So there exists an inverse. But why we want to write down this? Because this is the weakest argument, weakest criteria. And it implies that, so if there is a certain algebraic system that satisfies this one, then there will be a right inverse for A. And at the same time, this left inverse and the right inverse are unique and they are the same. So we can prove that. Okay, so we are going to prove that. Is that okay? But this is the minimal requirement that you can check whether it is a group or not. Okay, so let's take a look of what we claim. Okay. So we have this theorem. So suppose that this A star is a group. Is a group. Then, if we have a left inverse of A, so if B star A is equal to E, so we want to claim that if B star A is equal to E, then what? Then A star B is also equal to E. Okay? So if there is something that acts as a left inverse, then this item also acts as a right inverse. Is that okay? So let's prove this. So the proof, so because this is a group, okay, then B will also have a left inverse. Is that okay? So let's see be the left inverse of B. So we have never talked about anything called a right inverse. Is that okay? We have only left inverse. Now, consider this one. Let's consider a very long formula. Okay, consider this one. C star B star A star B. Okay, let's consider this one. We will see that this one is the same as C star B star A star B. Am I correct? Because we have associative property. Okay? And then what is it? What is it? B star A, by our choice here, B star A is equal to E. So this is E. Is that okay? E multiply anything is that thing. So we get CEB, which is CB. Is that okay? What is C star B? C star B is E. Very good. Because this is the definition of C. So this is equal to E. Is that okay? Look at this thing. What is C star B? C is the left inverse of B, right? So this is E. E multiplied with anything is that thing. Okay, so this is going to be A star B. Is that okay? And that's it. That's it. We have shown that A star B is equal to E. This is what we want. Is that okay? Okay? Is that okay? Okay? And then this shows that if something acts as a left inverse, then it also acts as a right inverse. And then we also want to show that an inverse is also unique. So there is no two left inverse of the same thing. Okay, that will also be easy. So this is theorem 1. Theorem 2 is so the theorem 2 is inverse is unique. Okay. So for instance, suppose that A has two inverse. Let's say B1 is an inverse and B2 is an inverse of A. or, okay, so suppose that, so let's say we have a proof here. Suppose that B1, B2 are both inverse. Inverse. Then let us consider this one. Let's consider B star A star B. And C star A star B. Okay. Now, sorry, we have B1 and B2, sorry. So this is B1, B1, B1. Let's say this is B2. Is that okay? Okay. So let's say B1 and B2, they are both inverses. So B1 multiplied with A is going to be E. B2 multiplied with A is also E. Is that okay? So EB1 is equal to EB1. Is that okay? So far, so good, right? But okay, if you look at this, so the left-hand side, it is equal to B1. No problem, right? EB1 is equal to B1. Right-hand side, this one, you use associative thing. So you have B2 multiplied with AB1. Is that okay? Now, we have shown that if something is a left inverse, then it is also a right inverse. So it is going to be B2 multiplied with E. And E is the identity. So this is going to be equal to B2. Is that okay? That's it. Okay. So actually, that's why. So when you are going to work with a group, you can just by your knowledge assume that there's an identity and there's an inverse, which is both left and right inverse. And the identity and inverses are all unique. Okay. So this is. I hope you like this definition so far. And then next time we'll look at a lot of interesting property of a group and see if we can apply group in some real life application. Okay, let's meet again next week. Thanks.